Hi all. So, we are already into the theory of optical waveguide. So, I start a new chapter and the title of this chapter is Optical Waveguides Theory and Design. First of all, in this lecture today, I will be discussing total internal reflection based Eigenmode solutions for slab waveguide. So, we have a clear picture about total internal reflections, and also we have shown that total internal reflection, in fact, it can provide 100% reflection at the interface when electromagnetic wave propagates from denser medium to rarer medium, and the angle of incidence is greater than critical angle. And that is a almost lossless internal reflection happens, and you can get very good optical waveguiding, dielectric optical waveguide. So, I would like to discuss today slab waveguide or planar waveguide structure based on TIR, total internal reflection, to solve eigenmodes, different eigenmodes supposed to propagate in the planar waveguide structure. So, here is an example of slab waveguide. So, you must know that this slab waveguide is normally not so useful for your photonic integrated circuit, because for photonic integrated circuit you need two-dimensional waveguide, two-dimensional confinement. However, for starting to understand the optical waveguiding etc., we will start with a planar waveguide structure. And most of the time also when you fabricate a photonic integrated circuits, you need wafers or substrate. And for photonic integrated circuit, specifically 3 different layers are very important. Okay. So, the bottom layer is called lower cladding, this is lower cladding, and this is middle one is the core, and this is actually upper cladding. So, this bottom cladding, core, upper cladding can be a suitable choice of material and suitable thickness. And in the bottom you can have your substrate, handling substrate, that can be suitable thickness, you can use that one, that will be substrate. Typically that substrate is in the order of 1 millimeter thickness, 1 millimeter, sometimes 500 micrometer and so on. So, there are popular platforms for photonic integrated circuits, and these platforms basically substrate or wafer we can commercially buy, you can commercially, there are manufacturer who can produce wafers for photonic integrated circuits. So, those wafers we know can be useful for photonic integrated circuit are mostly few popular platforms. Here I have just shown. First one is silicon uninsulator, and of course bulk silicon and silicon nitride. So, these are basically, we call it the substrate, not substrate, entire wafer can be called SOI substrate. Main thing is that it is basically, we technological point of view we will call that as a SOI platform or SOI technology, bulk silicon or bulk silicon photonics technology or silicon nitride photonics technology. Okay. So, these are all basically silicon based, these 3 green color things silicon based. And if it is a silicon uninsulator, you have a bottom substrate is of course silicon, and this so called core material, this core material is silicon, and then lower cladding material is silicon dioxide, sometimes it is called box, buried oxide, and upper cladding layer, this one can be silicon dioxide or ER. Native silicon dioxide you can grow on silicon, that same thing is good for silicon on insulator wafer. So, one can use that silicon dioxide. Obviously, you should keep in mind that for waveguiding purpose you need to maintain this condition, that refractive index of core material N1 must be greater than N2 and N3. It can be possible that N2 and N3 can be equal. In that case, we will be calling that as a symmetric slab waveguide. So, core region sandwiched between two identical lower refractive index material, upper cladding and lower cladding, that will be called symmetric slab waveguide. Otherwise, if it is simply just N1 greater than N2, something in this order, then we will be calling as a asymmetric planar waveguides. You should keep in mind that why we need N1 higher, because we want to confine light in this region. In this region, light will be confined and it can propagate along z direction, or if you want it can propagate also x direction, y direction. X direction it will not be allowed, it will be confined because of this type of arrangement. So, if you are launching light, this light can propagate in the either y direction or z direction freely. However, as a homogeneous medium, it is like infinitely extended yz plane, but along x direction there is a inhomogeneity is there. There is a core region where refractive index is higher along x direction, N1 region, and top cladding or upper cladding and lower cladding. So, this is just one example I have just given. Silicon, normally for silicon on insulator, the silicon crystal refractive index is in the order of 3.47, silicon dioxide is relatively less, 1.45, and then again top cladding also silicon dioxide or AR. So, if it is bottom is silicon dioxide, top is silicon dioxide, then it is a symmetric slab waveguide for SOE, and if it is bottom is N2 equal to SiO2 and upper is AR, then it will be called asymmetric. Similarly, we can have a bulk silicon where this core material is polysilicon. So, that is these things are chosen depending on the available technology, CMOS compatible technology, because all these SOE bulk silicon they are chosen so that you can utilize CMOS compatible fabrication process that we have discussed earlier. And again similar like SOE, the bottom cladding, lower cladding is silicon dioxide. Native oxide you can easily fabricate, you can form, and then you can upper cladding, that is N3, that will be Si2 or AR, you can keep it just bare. AR refractive index is 1 and silicon dioxide is 1.45 if you are operating at 1.55 micrometer. Similarly, there is another platform, well known platform, silicon nitride. Okay. So, their core material, the silicon the N1 material refractive index, that is silicon nitride, refractive index in the order of 2 at 1550 nanometer, and then bottom cladding can be silicon dioxide and top cladding silicon dioxide or AR, symmetric and asymmetric slab waveguide you can make on silicon. So, I must mention that these three things, this three material platform, it is written in the fabrication process almost standardized, and foundry semiconductor foundry is also adapting. You can fabricate CMOS compatible fabrication process line for photonic integrated circuits. CMOS and silicon is correlated. So, this is adapted accordingly. However, there are other interesting materials also material platform people started using because of different other type of advantages. You know that silicon for photonic integrated circuit purpose, it is not suitable for laser, okay, laser diode integration, and it may not be is the best material for high speed modulator. So, that is why people already explore and also going forward with other platform like lithium niobate on insulator. Lithium niobate, you know, we have discussed earlier, lithium niobate is a very good material platform for high speed modulator. So, the technology already developed to bond lithium niobate crystal with silicon dioxide on silicon. So, you can have your core material lithium niobate thin film, and then lower cladding can be silicon dioxide and upper cladding again silicon dioxide or air. So, this is also one platform people use, and this is for module, particularly for modulator purpose and some other nonlinear photonic application purpose, because lithium niobate is also known for nonlinear, very good nonlinear optic material. And then 3,5 compound semiconductor. So, 3,5 compound semiconductor like gallium arsenide, and gallium arsenide can be core N1 material, and upper and lower cladding can be aluminum gallium arsenide, because if you are just making alloy with aluminum, gallium arsenide and aluminum, some fraction of gallium is replaced by aluminum atoms, then refractive index reduces. So, that can be considered as a lower cladding. This is also lower cladding, can be upper cladding or lower cladding, you can just have a lower refractive index. Similarly, this gallium arsenide basically used for laser diode, photo detector, all those type of things. It is direct band gap semiconductor, it is useful. However, gallium arsenide laser, if you fabricate, typically the emission wavelength not satisfying your communication band 1550 nanometer, rather it is around 1 micrometer, less than 1 micrometer. So, that is why another platform is used also, that is called indium phosphide platform, that can be used as a core, and you can have indium gallium arsenide phosphide, another compound alloy, you can grow, technology is available, that type of wafers are available as a lower cladding N2, and AR or another layer of indium gallium arsenide phosphide can be upper layer. So, these are the platforms available, and if you use suitable technology available to you, then you can make different type of photonic structure, that can be active devices, that can be passive devices, that can be programmable devices, and some devices, some platform is more important, more interesting, because it can also integrate electronics. For example, SOI and bulk silicon, silicon and insulator and bulk silicon, you can co-integrate electronics as well as photonics. However, lithium niobate on insulator platform, you cannot co-integrate, your electronics chip will be separate. 3,5 semiconductors, 3,5 semiconductors you can co-integrate electronics also, but you know CMOS electronics you cannot integrate, some high power electronics, all those have different type of technology is possible, but normally people use these 3,5 semiconductors for separate active optoelectronic devices like lasers and photodiodes. Okay. Nevertheless, I would like to discuss that whatever this platform you get, and always you are getting these 3 layers in your hand already. Before you can design your waveguide structure and you can fabricate your waveguide structure or photonic integrated circuits, you need to know what is the wafer you are going to use and what is their refractive index in the core region and what is the refractive index in the upper cladding, what would be the refractive index of the lower cladding, and what is their dimension. Specifically, the dimension of core layer is very important, because there only you want to confine your light. So, these things known to you. So, based on that you can actually go for fabricating photonic integrated circuits. So, as you see, as you get your wafer, it is just simply a slab waveguide, because you have upper cladding, lower cladding and core. So, let us try to understand how light is confined at least one direction as you get your wafer. As you buy your wafer from manufacturer, you can do sometimes customized wafers also. You are already getting a slab waveguide or planar waveguide structure. So, I need to understand first how this planar for a given thickness, how this planar waveguide structure can be analyzed and understood, how light is confined in one direction, and I can understand the modal picture just simply by total internal reflection method, whatever we have learned so far. Using that thing we can actually we will be able to understand the propagation in 1D waveguide. Then later on we will be moving for more rigorous wave equation theory, Maxwell's equation, to get more clear picture. For the moment, just to get a modal picture, waveguiding mode, how light is confined, that picture will be easier to understand using total internal reflection methods. Okay, let us move on. So, this is the picture. I just replicated this wafer 3 layer system. This is your N1 core region stretched between this region x less than d 0, that means thickness is d, that is called as a waveguide core, and your lower cladding refractive index N2, that is this region, that means x less than 0, interface is always your yz plane at x equal to 0, and another interface also yz, another yz plane at x equal to d. So, this one, and we are considering this yz plane is infinitely extended, for example, for the moment. As I mentioned earlier, that in this type of situation you can think of that light is free to propagate along y direction as well as z direction, only it will be confined along x direction because of the total internal reflection here and here. Why total internal reflection will take place? Because we have chosen this condition, refractive index of this region, if you see N1 greater than N3 and N1 greater than N2. So, any wave in this region, if you are launching here, if you somehow get a angle which is greater than critical angle, it will get total internal reflection will take place. Similarly, if something comes here, so if this theta is greater than critical angle in this interface, then it will be totally reflected. Okay. So, this is the picture, we are just considering D, okay, and we will try to understand how one dimensional confinement is possible and what would be the mode solution. Okay. So, this is the picture we have shown, that a beam, parallel beam is coming, as we have already discussed during total internal reflection understanding. So, ray is coming planar wave and going in this direction, and total internal reflection can happen. This theta you can consider such that it is greater than critical angle, lower critical angle, lower interface critical angle for the lower interface, and also it can be greater than critical angle for the upper interface. You know, critical angle you can define, for example, upper interface, here in this interface critical angle would be sin inverse N3 by N1. Sin inverse N3 by N1 is the critical angle for the upper interface, and theta CL is the critical angle, that is sin inverse N2 by N1, that is in the lower interface. If your this angle is greater than both lower cladding critical angle and upper cladding critical angle, so I can say total internal reflection in the lower interface as well as upper interface, upper interface, lower interface. So, all this total internal reflection I can see, and you can think of the another ray, it is another completely opposite direction, it is this direction you are considering, another angle you can consider also theta here hitting here. So, here also it can happen TIR, and then TIR. So, in this way you can get some way total internal reflection in both interfaces, and certain angle entry should actually satisfy certain angle, so that this is satisfied. Okay. Next is, you see, this is the material medium where refractive index is N1. So, corresponding any wave vector, that is a wave vector constant, I would say wave propagation constant, I would say, that is we already discussed earlier, that is 2 pi by lambda N1. Lambda is the incoming ray, whatever the light is coming, electromagnetic wave is coming, that has a lambda wavelength in free space, and N1 is the refractive index, that is a dielectric material, of course. And even though we are considering this a semiconductor platform, 3 layer platform, but we should choose this lambda such that lambda is transparent, that photon energy should be less than the band gap, and so that it can see like a dielectric material medium. Okay. So, this is the propagation constant in core region, this is the propagation constant in the lower cladding region, just 2 pi by lambda N2, and this is the propagation constant in the upper cladding region. Good. So, next thing is that, okay, suppose this is your theta. So, this is your theta suppose. Now, if I try to get what is the, this is suppose k1 vector I am considering. So, what is the x component k1x? K1x is k1 times cos theta. So, 2 pi by lambda cos theta. Since you have another reflection coming here, right. So, it is also can be considered as a k1 here, this vector we can define, then it will be also k1x will be there, and here also k1x is there. So, in that case I have in this total internal reflection both interfaces, if it is happening k1x, it can have plus 2 pi by lambda n1 cos theta, 2 pi by lambda n1 times cos theta, that is the x component, and since it is opposite direction also one component is there, we write plus minus. And if I just try to see the longitudinal component k1z 2 pi by lambda n1 sin theta. So, this is the longitudinal component. In the core region I know that what is the transverse wave vector component and what is the longitudinal wave vector component. You can think of identical situation for the another ray coming in opposite direction here. This also you can consider, this can be also similar theta. Okay. So, here also you can see k1x positive and here you can see k1x negative, and here also decomposition you will be getting k1z. So, longitudinal component is fixed for all, but you have counter propagating. If you are just independently thinking that the electromagnetic wave having a propagation constant k1x component, then it is a counter propagating wave is there in that direction. So, for good, then if I just try to find out what is the k3x, k3 is this one. Okay. K3x earlier we have discussed that in case of total internal reflection we can think some kind of imaginary transmitted wave vector, which one having longitudinal component ktz, which will be continuous like this one. So, here I will be considering here this k3z, k3z will be equal to k1z because tangential component will be same, but normal component will have a imaginary. So, during total internal reflection normal component will have imaginary value, and that value we have derived earlier also. If theta is the angle of incidence here we are considering, then n1 by n3, that is the in this interface n3 n1 refractive index contrast and sin square theta minus 1, and since this is a positive value for theta greater than theta c, okay, theta cu, right. So, we can say that j 2 pi by lambda k3. So, 2 pi by lambda is the normal wave vector in the free space, and n3 times this one we just write kappa 3, okay, j times 2 pi by lambda kappa 3. So, that is the imaginary part. So, we know that that is how the field will be decaying in the x direction, because of the x component is imaginary, that will be attenuating. So, any wave vector component is real, that will be actually like a travelling wave, it will be generating, that we have discussed earlier. Okay. So, similarly we have k2x in this direction, if it is I am just defining k2x, that should be also imaginary, 2 pi by lambda kappa 2. Okay. So, that means in this region also it will be decaying, anywhere it is total internal reflection happening, that will be decaying. Okay. So, I consider that some field will be there in the top side and upper side because of this condition for the total internal reflection. Now, this thing, because it is decaying, it is actually normally we call it as a evanescent field. So, that field is existing, but that field is not carrying energy along the x direction. X direction it is decaying, that is actually for our photonic integrated circuit. So, those who are studying waveguide, waveguide theory etc., normally this type of decaying field is they call like a evanescent field. Okay. So, field is there, but energy is not flowing in the x direction, but that field will carry energy whatever field is there in the z direction, because we know that here k3z will be there, here will be k2z because it is medium 2, and here is k3z component will be there, and k1z is there, they are identical. That is why k1z can carry energy in this direction, k2z also in the cladding region also carrying energy in this region, and K3Z also will be carrying energy in this direction. So, that means the field exists in the second media, but it is not like a propagating along x direction, not propagating along y direction, but it can contribute whatever field is existing there, that fraction of the field also contributing energy propagation in the z direction. So, that region also very much part of the waveguide, that evanescent field region, including the core region. You have some extended evanescent field, that evanescent field also propagating with a longitudinal wave vector k3z here, and here will be k2z, and here will be k1z, and as we know tangential component is always continuous, tangential component of the wave vector k1z, z direction tangential in the interface. So, they are continuous. So, you can consider that power is or energy will be carried by the evanescent field in the z direction, propagation direction. I am not considering the field propagation along y direction, because y direction I am just not considering at all, anything happening I am just ignoring for the moment. Okay. Now, I just mentioned this k1z, what I discussed in the previous slide, equal to k2z longitudinal wave vector, that is tangential component in medium 1 in the core region, longitudinal component tangential component in medium 2 here, and tangential component in medium 3, they must be equal, and we give another symbol, we call it as a beta, propagation constant. We can say the effective propagation constant along the propagation direction. That will be actually nothing but k1z, whatever the k1z value is there, I am just written there. Whatever k1z, that will be k2z, that will be k3z. So, we write like this. Fine. So, these are the things we need to understand more rigorously in future. Okay. Now, we know that when total internal reflection takes place, there is some kind of phase change happens, because that reflection coefficient become complex. So, when reflection coefficient become complex like this, A plus J B gamma T or gamma T M, we consider like that. If it is complex like this, A minus J B by A plus J B, that should be 1 into e to the power minus j phi, something like that. Total internal reflection will take place, but it causes some kind of phase. That phase I am just writing down here, just to give you a clear picture what happens. So, now Eigenmode solution, what is that? This is very important, is note down what I have written here. You have the k1x, and that has a plus k1x and minus k1x. You have forward propagating wave and backward propagating wave along x direction. So, if you just concentrate on that wave vector k1x, and that somehow creates some kind of standing wave pattern along x direction, then that can be considered as a mode. How that is possible? We know any standing wave, suppose you are considering a cavity, simple Fabry-Perot cavity or a resonator cavity. If any wave propagates here and this direction and comes back, and if comes back with 2 pi phase shift, round trip travel, if it contributes 2 pi phase shift or integer multiple of 2 pi phase shift, then suppose this is a propagation constant, propagating wave propagating in this direction and coming back this direction. So, if it is L, so round trip phase is propagation constant, it is a beta into jet, right. So, propagation constant k and round trip is L 2 times 2 k L. If this 2 k L is becoming 2 m pi, then we can consider that is actually somehow creating self consistent and resonance standing wave is generated. So, similarly, I can say that this k1x when going first reflection here, this is going, that means kx component reaching up to this point, taking energy to this point, and then it is flipping back, then it will come back again. So, it will, when it is coming back to this point, that means k1x actually completing one round trip. So, from this point to this point, k1x actually helping phase completion along x direction is one round trip total round trip. So, if I just consider k1x times 2d, d is forward direction and reverse direction. So, that is the round trip phase, but from here to here reaching, it is undergoing, if we consider this point A, it is undergoing one total internal reflection and another total internal reflection here. So, that means, when this point to this point, this is A and this point A and B point you consider, if coming A to B, if you want A and B exactly identical, that means the k1x whatever round trip phase is contributing, along with that you have to consider whatever phase change happening because of the total internal reflection, and that is actually stopping the wave propagation along x direction. That is upper interface we are considering minus phi u and lower interface we are considering minus phi l. So, for example, for one round trip you have this is the phase for k1x and additional phase phi l and phi u lower interface and upper interface. So, since they are minus sign, we have seen that actually you remember that that is actually 2 tan inverse n1 square root n1 by n2 square minus n square theta, so on, that tan inverse minus sign is there, you could use that minus sign. So, whenever you will be inserting this phi value, that time only we will be considering plus sign, that exact value we will be putting. So, this is the value, this is the equation we can use for mode solution. A round trip phase shift 2 k1x d minus phi l minus phi u lower interface upper interface, and this round trip is 2 pi times integer, then that will be a solution for modes where m can be considered as 0, 1, 2, 3 and so on. Okay. So, this is called Eigen solution for guided modes. So, written down here Eigen solution for guided modes, where if you are just considering T polarization, you know T polarization, where in this configuration reference frame electric field will be oscillating only along y direction, only y component is there, and magnetic field will be in the xz plane. That is one type of polarization, we call it T polarization, and I just we normally distinguish T and Tm just to take advantage of boundary conditions and without compromising any violation to satisfy Maxwell's equation and wave propagation. So, if I consider these 3 components, that is good enough to carry energy, and another 3 set of components called Tm, that also good enough to carry independently energy. So, we can treat them separately if all the 6 components are there. So, we can take this set of components and treat them because it actually it satisfy one type of boundary condition, because Ey is the only electric field that is tangential to the interface. Okay. So, for Ey we know that is the phi Te in the lower interface. Lower interface means you have n1 refractive index and n2 refractive index, that comes in here tan inverse this one, n2 n1 by n2 n1. And if you are considering upper interface, whatever the phase is changing for T polarization, n2 will be replaced by n3, because here interface is n3 upper interface. So, if I insert this one here and this one here, then that solution, if I am getting at all some solution, that will be corresponding to T polarization, because this phase change in the interface, whatever phase change occurring because of the total internal reflection, that has been considered for T polarization. Okay. So, now I am just after substituting how it look like. So, 2 times k1 cos theta, I have just written cos theta Tem. You will be understanding why we are putting that. So, 2 pi by lambda n1 cos theta m times d. So, that is what you wanted to get, right, 2 k1x d. So, 2 times k1x equal to 2 pi by lambda n1 cos theta, that is what we have written. T I have put because I have used the phase change phi u and phi l for T polarization, and m I have written because this theta solutions I will be getting for m equal to 0 and m equal to 1, for m equal to 2 and so on. So, this is the left hand side, and right hand side we have 2 m pi, and then phi u and phi l I have taken right hand side. So, whatever the value here, if I take phi l and phi u this side, that will be 2 m pi plus phi l plus phi u. If it is TE polarization, I will be writing TE and TE. This expression I will be writing. Okay. So, that is what we have written. Of course, you can just think of cancelling this 2, 2, 2, then you will be getting a very nice equation. So, left hand side theta TE, right hand side also theta TE is there, and you can solve, because for a given m if you are putting m equal to 0, you will be able to solve theta TE 0. That is a one solution for theta TE. That means, your theta TE solution is now discretized, because m is discretized, right hand side you are getting solution, you are putting m equal to 0, you will be getting one solution for theta TE. You are putting m equal to 1, you will be getting another solution for theta TE. So, this is very important to conclude. This actually ensures that any theta greater than theta CL and theta CU, greater than the critical angle in the lower interface and upper interface, is ensuring total internal reflection, but that not ensuring whether it is a guided mode or not. That guided mode ensurance is coming through this equation, because round trip phase accumulation because of the transverse component of the wave vector, that should satisfy some standing wave or resonance condition. So, that condition is giving this one, and where from we find that the theta value is now discretized. So, all theta value will not give you standing wave pattern along x direction. So, all theta value you will not see any confinement along x direction. Only a discrete solution for m equal to 0, m equal to 1, m equal to 2, m equal to 3, using this equation you can get a solution. Okay. So, now if I just try to get for TM polarization you know this is other way. So, your magnetic field is having only y component Hy, but electric field is in the xz plane. So, other things. So, in that case also you can get a similar solution, only thing is that this phi L and phi u you have to consider for TE and TM. Okay. So, earlier you have used for TE equation, now you have to use for TM. So, the solutions come similar thing, but you will be getting different solution for theta TM, because the phase equation is different and the interface, because of the total internal reflection, whatever phase it is acquiring, that will be different for TM polarization. For that purpose you will get different set of solution for theta for TM polarization if components are like this. So, you will get two set of solution, one for TE solution, another for TM solutions, and their equations are slightly different. So, different type of theta values you will be getting, and m actually again it is defined for 0, 1, 2, 3, 4 for TM polarization. You can put there n also another integer, because just to distinguish T and TM. Good. So, now we know that well theta TM, which particular theta value are satisfying to create a standing wave along x direction, and that will be considered as a mode. So, what is next then? So, now I have written that thing. Okay. This is the Eigenmode solution for TE polarization, Eigenmode solution, and I have written that K1z, K2z, K3z even for TE polarization, that will be equal to this one, beta propagation constant, right. This is the thing. Next, you see K1z m for TE polarization, K2z m for TE polarization, that means field components are like this, and K3z that will be called as a beta m TE. So, instead of beta, because it is polarization sensitive now, you are just considering which polarization, depending on that which Eigenmode solutions you are solving, because you have different for TE polarization you have this Eigenmode solution, and for TM it will be different. So, beta TM you know this is n1 sin theta, you are solving theta m TE here. So, I can find a theta m, theta 0 for TE polarization, theta 1 for TE polarization, theta 2 for TE polarization, blah blah blah. So, that will be for m equal to 0, this will be for m equal to 1, this will be for m equal to 2. So, I am just putting m value here and corresponding theta TE value I can solve, and using that theta t value I can find out beta. I can find out beta 0 t polarization, beta 0, discrete values of beta propagation constant also. Beta 1 for t, beta 2 for t, beta 3 for t, and so on I will be getting. So, that means longitudinal component I will be also getting discretized. Okay. So, one thing is that the k1x first it is discretized depending on the, this is the Eigenmode solution, this is basically the k1x, right, k1x time d 2 times round trip, that k1x is discretized because theta tm solutions you will be getting different because of the m. And once k1x is discretized, you can say that k1x square plus k1z square, that should be equal to k1 square, because k1 is equal to, you have ax, you can define like ax, k1x plus ay, az, k1z. So, in the xy plane, xz plane you are considering the k vector, right. So, I can have a propagation constant also I can get, and whenever I am writing, you know, 2 pi by lambda by n beta expression, it is like that 2 pi by lambda n1 sin theta m. Normally, if it is a homogeneous medium of n1, the propagation constant would have been 2 pi by lambda into n1, but it is in the waveguide, you have to multiply longitudinal direction, the propagation constant it's sin theta TEM, whatever solution comes you have to consider this one. So, instead of n1 you are using this one, n1 times sin theta solution, whatever the solutions you are getting. These sin theta solutions I will be calling as a effective index, n1 times sin theta, that is not n1 exactly, but it is n1 sin theta, effective index. So, since theta t, I say that I have a set of theta TE 0, theta TE 1, then theta TE 2, then theta TE, these are the solutions I am getting corresponding to m equal to 0, m equal to 1, m equal to 2, m equal to 3. So, that means all these discrete values if I put, I will be getting n effective also discretized. So, those modes also will have n effective 0 TE polarization, n effective. So, first m is actually corresponding to theta solution 1 TE polarization, n effective 2 TE polarization. So, you will be getting effective index of the different order of guided mode. So, m actually, this m entry actually defining individual propagating modes by giving the discrete solution of theta t, theta m you are getting, right. So, once you get discrete solution of theta m, then you get a discrete solution for k1x and discrete solution for k1z. k1x actually confining a discrete nature of the actually a specific standing wave pattern corresponding to one discretized k1x will give one particular standing wave pattern along x direction, and corresponding k1z will be that pattern, how it will be propagating along the z direction, that will define. So, every m entry will give you set of k1x and k1z. k1x is giving a pattern along x direction, field distribution, and k1z how that field will propagate along z direction, that will be giving. What would be the phase velocity of that pattern? Because that will be coming in your phase from, that is the propagation constant, that is a real, by the way. So, real part of the propagation constant, that means it is oscillatory, this z direction it will be oscillating and moving, and x direction because it is counter propagating standing wave giving you mode. So, that is the case. And beyond core region, upper cladding and lower cladding, because you have the imaginary propagation constant vertical direction, so that will be attenuating. So, I can say that standing wave pattern I will be creating here x equal to 0 to d, this region, some kind of oscillatory standing waves, nodes, antinodes will be coming, right. So, when only one antinode will be coming, then it will be called fundamental mode, 2 will be coming, there is a first order mode and so on, it will become different type of mode, and each of them will have individual longitudinal component along z direction, that will be giving you phase constant or phase velocity. Okay. This is all about for TE polarization I am discussing. So, now the solutions for this TE polarization, TE guided modes, I can say that because you are getting a standing wave in the x direction. So, I can say that a mode solution, I am not considering y variable em x z t, because y direction you can consider it is infinitely extended, it is constant along y direction. So, electric field is only a function of x, z and time. Okay. So, if it is I would like to know, because z direction it is propagating and x direction you are getting some kind of standing wave pattern, some kind of resonance because of the k1x. So, you see that electric field distribution will have a some kind of x distribution, you will see some kind of function. So, you see this type of functions we could predict by considering a plane wave getting total internal reflection back and forth, upper interface and lower interface. And then here you can see that you for a particular mode, say m, for m equal to 0 you will get one particular distribution, m equal to 1 you will be getting another particular distribution along x direction, m equal to 2 another particular distribution along x direction. This y is nothing but your y component, I mean to say y component for TE polarization you will be getting. And this pattern, this y component means vector is along y direction, and this entire pattern it will be propagating with a phase velocity omega by b times z. So, phase velocity will be ph for mth mode, that will be omega by beta m t, we can say. If it is TE polarization we can say phase velocity. So, normally since m equal to 0 you will get one solution, m equal to 2 another solution, 3 another solution. So, each mode will travel with a different phase velocity. That is very interesting, because in the waveguide you can get a different set of solutions, but all of them will travel with a different phase velocity, different phase constant and different distribution pattern also. So, this is all about mode. So, when you say a certain specific mode along certain direction x direction, and that pattern is actually unique and it maintains along the propagation direction as it propagates along the z direction with a phase velocity, that is omega by beta phase velocity. So, this beta m is nothing but whatever you are getting this longitudinal components, because k1x is contributing to standing wave, k1z actually contributing to the energy propagation along z direction. So, this is how the mode picture we can understand, at least just simple total internal reflection, ray optics picture, just resonance condition, standing wave and components, propagation constant component, etc. We starting from the just plane wave total internal reflection in the interface we could somehow, and so it is I have not considered any compromise so far to solve this type of different type of mode solutions. Just this arrival, this type of distribution, we have to just, we know that what would be the distribution, but exact distribution you know that this will be like a standing wave, here it will be created and outside it will be exponentially decaying because of the imaginary part. So, but in the, because Ey component is tangential, the field strength in this lower interface and upper above the interface and below the interface, they should be continuous. So, you can use the boundary conditions and to find out the entire profile solutions. I hope it is clear. Next is same thing I can think of for TM polarization. TM polarization, again as I mentioned earlier, the electric field will be in the xz plane and magnetic field will be normal direction. So, that is the tangential component, electric field, magnetic field. So, for that purpose we have another set of solution, eigenmode solution, because you are entering phi L T, right, Tm, phi L Tm or whatever I consider, phi L subscript or superscript whatever, and phi U Tm. We have to put 2 tan inverse, all the value will be there. So, this function will be slightly different, here it is n2, here it will be n1 and n2 here. So, this n2 and n1 will be interchanged. For upper, this is you are considering lower interface phase change, and this is upper means n3 coming, n3, and here numerator denominator interchange for TE and TM, that is the difference, just to keep in mind. But you can I think I have shown how to derive, how to starting from Fresnel equations, when theta is greater than theta c, what would be the phase difference, phase change occurring at the interface, that you will be able to derive using that equations. Already everything is should be Tm, we should write a Tm, right. So, in that case you will be getting longitudinal direction, all the solutions, effective index solutions you will be getting, and similar to that you will be getting a mode field solutions, but here we have written instead of TE polarization I have just considered electric field, but here we are considering magnetic field, because magnetic field is the tangential. So, all the boundary conditions in the lower interface and upper interface you can use magnetic field, because magnetic field, all magnetic field or electric field in the boundary interface they will be continuous, tangential component will be continuous. So, only component Hy for Tm polarization, that must be continuous across the interface. So, you can use that boundary condition to make some continuity here and there and there, and you get a clear field distribution picture. But thing is that you should keep in mind, we are actually finding the only one component for TE polarization. What about other two component? How to find other two component? You go back to Maxwell's curl equation. From that curl equation, once you know, you just insert electric field, only electric field component known to you of this type of solution, for example, then you insert there, then you get other components easily. Okay. So, similarly, for magnetic Tm polarization, you have the solution for Hy, y component is there. So, again use curl equation, one of the curl equations you use, and then you can find other components Ex and Ez. So, all the components you will be able to solve for both separately for TE polarization and for Tm polarization, and you can get whether what sort of, how many modes you can get. For example, next thing we will be discussing that, okay, I know that M can be 0, 1, 2, 3 and so on. So, how many more solutions, how many solutions I would be able to get, because the integer means you can start from 0 to infinity integers. So, you will be able to get infinite number of solutions, but all these infinite number of solutions will not satisfy confinement along x direction. So, you have to ensure the confinement along x direction. So, all the solutions you have to check whether that is giving you confinement along x direction or not. If it is not giving confinement along x direction, that is not a guided mode. You have to ensure the confinement along x direction, and up to the value, suppose up to 3 you are getting a solution, getting solutions which is giving well defined confinement along x direction, then we can say that there are 3 modes can be guided in this waveguide. If it is up to m equal to 5 solutions are giving confinement along x direction, then we can say that 5 modes are supported by the waveguide, and beyond that it will be, even if you launch light at certain angle, solutions you will be getting, but that will be leaked, that will not be confined, that will be somehow the angle must be is less than the critical angle in the interface, that is why it is not confined. Okay? Fine. So, I will be now discussing how to get a solutions of the number of modes for a given d value thickness, for a given n1, n2, n3 and lambda. I would like to know how many modes it can support and how to define d, so that I can say that it will be supporting only one mode, or I can design d values to allow desire 5 modes. I desire, for example, 5 modes to be guided. So, I need to find out what is the value of d required for a certain operating wavelength lambda. So, those type of things I will be just giving some examples like silicon on insulator platform maybe, and we will try to find out the values, how to solve those values. It is not so easy, trivial that you can directly get a simple analytical solution from here directly theta Tm, because it is something like this equation. If you look, left hand side also theta T is there, right hand side also theta value is there, theta is the variable. So, you cannot get something like theta very easily, theta something like that right hand side. If you would get, then analytically you just insert the value and you can calculate easily what is the theta value. and this type of equation is called transcendental equation. Easily you cannot get some kind of analytical expression for theta. Okay. So, we need some kind of graphical method to solve these two equations and try to understand how to estimate the number of modes and their field distributions and their propagation constant or effective indices or phase velocities for a given wavelength. If you change the wavelength, situation will be different. So, those things we will be discussing in the next lecture. Thank you very much.